Hi, my name is Rogier Lommers. I come from Nijmegen, a town in the east of the Netherlands, and I work for Bol.com 11 years already as a principal tech lead. And for those of you who don't know Bol.com, we are one of the biggest online retailers in the Benelux. We started in 1999, and we are selling like about 34 million of products on our webshop. We have a website, of course. We have an app, and we act as a marketplace for where other companies can sell their products. So yeah, that's us. Today I'm going to discuss three main topics. First, we are going to discuss vertical and horizontal scaling. Then I'm going to tell you how our asset pipeline works. So how do we put all the product images on a website? And I'm going to tell you about our lack of horizontal scaling back in the year 2019. This one. If you have questions during the presentation, just shout. I always think that works best. So, having said that, scalability is important, right? If there's something which I've learned in the past 12 years, then it's about growth. You need to be able to handle the load. Today's load, in terms of page sizes, for example, is tomorrow's regular load. And this became more important by the years, and I want to give you a very simple example for the Dutch people here. Who is this? Yes, I am not the only old person here. Indeed, this is Bulletje. You can know this person from the Soundmix show. It was a game show, a television show back in the 90s, I guess, where kids could play back their favorite singer. So you were sitting on the couch with a cup of Nibbits chips, and suddenly you could vote using a good old landline. You could vote for the best performance, right? But suddenly all lines were dead, so no one was able to vote again. The number of people voting, so the number of people calling in, was simply too much. Luckily, they could solve it back then by adding more operators to the phone system, so problem solved. But yeah, this is a classical example of a scaling problem. And in 2019, we had a similar problem. So back then, we were running our workloads not in the cloud, but in our own data center. And it wasn't built for horizontal scaling. No, it was good old-fashioned way. 19-inch racks, a lot of them. Provisioning happened through rack tables and Puppet. We ran them on VMware hypervisors, and we deployed a lot of virtual machines. Each machine having its own role, and that role represents a Java or a Go service. Pretty straightforward. But this suited us best for a long time, but in 2019, things became different. Because of our services and hardware needs were growing, we came short at some point. And especially during certain periods of the year, for example, Black Friday or other Sinterklaas, there were moments when you needed a peak of additional hardware. And we could not deliver that. So in short, we were not optimized for horizontal scaling, we were optimized for vertical scaling. I don't think everybody really knows exactly what vertical scaling is, therefore a nice example. Take a look at this soccer field. Now imagine you are the lucky guy who needs to mow the lawn. So what do you do then? You buy a lawn mower. Here it is, a very nice piece of equipment, but soon you realize that it would take you a while to mow the lawn, right? So you buy a bigger one. And you start the engine, mowing the lawn, but the weather conditions are good. A bit of rain, sun, the grass is growing, it's growing faster, and you cannot keep up. So you buy the biggest model you can find online, you go all in, but then the soccer players, they again start to complain that you are not doing your job fast enough. So what do you do then? Now this is called vertical scaling. You want to go faster, then you buy a bigger mowing machine. In terms of tech, of course, it's about adding more CPU, adding more memory, more bandwidth, etc. In 2019, our data center was built for this, for vertical scaling. Back to our soccer field. So we were still not going fast enough. And then you become creative, right? You already had the biggest machine available, so you cannot buy a big one. Instead, maybe you should try to buy a few smaller ones, a bit more. They are cheaper, they are more available, easier to handle. And then you think of a construction with some duct tape and some metal bars and you tie them together. Let's see what happens. There they go. So your construction is working. And in about 10 seconds, you have mowed the whole lawn. And the best part of the story is that they scale horizontally, right? For example, if you want to go 2 times as fast, then you simply add more. There they are. Now let's see how it goes. Let the mowing begin. 2 times the number, and indeed, this happens now in 5 seconds. And that's quite an improvement, right? So this is horizontal scaling. And that's what we do nowadays in the company, but yeah, nowadays we would run more pods in the Kubernetes cluster. You use kube control and you add the number of replicas and then you're ready to go. But let's step in our time travel machine because I'm now talking about 2019 when we were not having Kubernetes, we were not having Istio, not all the goodies from having a service mesh. No, we only had our VMwares, our virtual machines provisioned by our operations department. But we also had a lot of assets to process. We had 260 million assets in our database. And assets for bol.com are images, documents, PDF files, videos, all kinds of assets. And on a regular day in 2019, our partners delivered around 80,000 new assets on a daily basis. Yeah, we need these assets for our channels, shop, mobile, web, marketing, external applications. Basically, we use assets everywhere. But how does this work exactly? How does an asset from being delivered at the back all the way up to the front, how does it work? And I will explain that to you. So from now on, let's focus on this Philips razor blade. In general, there are 5 steps this razor blade will go through. It all starts with downloading the asset. Then we try to do a deduplication, because we might already have this Philips razor blade. Then we extract some metadata. Then we do the actual rendering. And the last but definitely not less important step is the actual serving to our customers. Now, for each step, let's discuss it quickly. The steps are tied together using an event queue. This means that the result of the first step automatically triggers the start of the next step. And this, of course, gives us a nice separation of concerns, and basically it gives us a resiliency strategy. Back to the razor. So it starts with the content supplier delivering us this image, and it can be through our API or through a secure FTP server. And from there on, we put it in an S3 compatible storage bucket. And that's it. Pretty straightforward. When this process is done, like I said, it triggers a message on an event bus, which takes care of triggering the next step, which is deduplication. And a big chunk of those 80,000 assets which are being delivered every day, we already have them. So we need to find out if that's the case for this razor blade. When we started with deduplication, we tried to calculate the so-called MD5 hash. So a very simple byte array from a physical byte set on disk. And yeah, of course this works, but you can have the same image from an asset in different resolutions, right? And that would mean a different MD5 hash, and then the algorithm thinks, hey, different hashes, okay, different razor blades, which is clearly not the case. Luckily, there's an answer for that, and it's called the p-hash, the perceptual hash. So we improved the deduplication step by implementing the p-hash. So instead of calculating an MD5 hash, you calculate the p-hash. And what does it mean? You first convert the asset to a grayscale image. Then you resize this all the way up to 8 pixels by 8 pixels. And then you create a byte array and you calculate the numbers of differences, so the different bits, which gives you the Hamming distance. And that's a powerful value because the lower the Hamming distance, the bigger the chance that the two assets are equal, right? Yeah, so far for duplication. The next step in our image pipeline is about extracting the metadata. Because images contain very valuable information for us. Think about topics like the orientation. If a product is visualized inside its box or outside the box, detection of brands, of logos, of the most dominant colors of an image, but also nudity detection is something we automatically extract. Here's an example. So we use trained models where we, for shoes, for example, determine if a shoe's nose is pointing to the left or if a shoe's nose is pointing to the right, because in this case there are multiple shoes for the sizing table, and for a good customer experience you want all the noses to be in one direction. So that's typically something we do by automation. Other examples, like I said, are the fact that a product is shown inside or outside the box. You can very easily train a data science model on doing this task. Oh. Here is an example of our logo detection. And this one, I liked it a lot when we implemented it. It's about extracting the most dominant color from an image. And we use that to so when we render the page, we first put the most dominant color inside the div elements where the images eventually will be loading. So it's kind of a lazy loading concept. You start with the colors and then you replace the colors with the actual images. Last but not least, the nudity detection. So used for applying the adult filter. Yeah, speaks for itself, I guess. We store all these extracted metadata pieces of information inside a NoSQL database. And that's it. The next step is the actual rendering. So the supplier sent us his razor blade. From now on, we did deduplicate and checked if we already had the razor blade. We extracted some metadata out of the image. This step is about creating web-optimized versions of the incoming asset, of the incoming image. Because, as you can imagine, content suppliers, they give us very high resolution TIFFs, BMPs, JPEG, PNG, WebP, you name it, and I've seen it. And for obvious reasons, we want some kind of consistency in what we serve to our customers, and that's where this step is for. We didn't build it ourselves, because you don't want to build this yourself. There is the mother of all tools for this. It's ImageMagick. At first, we tried to do it ourselves, but don't go there. Trust me, it's hell. We now have written a very simple Golang wrapper around the C bindings of ImageMagick, which does the trick. When the web-optimized versions are done, we store them on disk, 2019, so we were still talking about disks instead of buckets. And a disk back then was nothing more than an NFS share on a NetApp instance. Due to the fact that we have literally billions of images, we needed to apply some sharding. We made use of our global ID, which is our unique identifier for a product within the company. And by using the first 5 characters of the global ID, we could create a directory structure, and which allows us to not be in conflict with the maximum number of inodes on disk. So yeah, that's it. The last step is indeed serving out the asset to our customers. I think we can all imagine how it goes. It's Nginx. In front of Nginx, there's a varnish cache for speed optimizations, and Nginx is serving the files out of that directory structure, which I discussed earlier. Nowadays, of course, we have a CDN and we make use of cloud edge functions, but yeah, 2019. This is what it looks like from a client perspective. There's a URL pointing to our Razor blade. It's being served by the Nginx service, who gets the image from disk, and so far our image pipeline. Now, back to the Razor. There it is. Because, so now you know how the Razor flows through the landscape. But what I didn't tell you yet is that sizes are quite important. Time to first byte is crucial for your page conversion, right? And a lot of studies, they all tell the same. They have a shared conclusion: be careful with big images and be careful with big image sizes, right? So it's fair to say that everything above the 5 seconds of load times means a disaster in conversion. So you want your images to be small, but of course there's trade-off when it becomes an image too blurry, too ugly, too whatever. Trade-off, size, quality. So what do? And then suddenly, Google announced the Gatsby algorithm. I think Gatsby is the way to pronounce it. I haven't validated that, so maybe if somebody knows, I always call it Gatsby. So what is Gatsby? It's a new way of doing image compression. It's an open source JPEG encoder. It comes as a static binary, so an executable file. You can run it on your Mac, on your Windows PC, on Linux. You can run it everywhere. And Google claims to deliver 30 to 45% of smaller image sizes. That's quite a reduction. And then without loss of perceptual quality. Now, back to our Razor machine. There it is. Here it freshly came out of our render pipeline. So ImageMagick made this image. And as you can see, it's 176 bytes in size.
Is it JPEG?
Yeah. So it's 170 kilobytes in size. And now let's apply the Gatsby algorithm. Here I did it on my MacBook. And as you can see, it's now crunching, it's applying models, it's doing all kinds of Google things. Google is good in this stuff. So yeah, it tries to apply models, and then it self-evaluates, and it tries again, It's not really interested for now, but the fact is that it takes a long time, right? So it's, there it is, 30 seconds, and then you have your additional image, which is 116 kilobytes. So that's a decrease of 34%, which is big. And I personally cannot see the difference between left and right. So it's good to do this. So yeah, we thought we were clever. We already had that loosely coupled architecture using that event queue. So why not add an additional step? Straight after the rendering, let's apply the Gatsby algorithm, right? It sounds quite simple, but then, bam. Everything was overloading, queues were piling up. Simply too much work. The Gatsby process took too long. We have service level agreements with our content suppliers, and we couldn't meet them anymore. So we had to do something. So yeah, we had a problem. So in fact, like I said in the beginning, each day we receive 80,000 new assets, and 10,000 of them were new. So after deduplication, we still had 10,000 assets which flow through our image pipeline. On average, 30 seconds. Gatsby, if you calculate it and you only assume that you have one core, so single-threaded, I know it's not totally fair, but it would mean that it took 3.5 days to apply the Gatsby algorithm, which is undoable. Yeah, I keep repeating myself. It was 2019. We couldn't temporarily and quickly add more hardware because of reasons. But we needed that. We needed that to, first of all, apply Gatsby to the new incoming stream of assets, but also for our backlog, right? We already had that 216 million renditions, JPEG files in our NFS share. I didn't know an answer, so every time when I don't know an answer on a question, I go running. And just shut down my brains, run for a while. And it was near this location on the dike in Nijmegen that I thought, hey, it doesn't really make sense, right? It's such a simple task. There's a binary, there's a JPEG file, you run it, you wait for 30 seconds, and you have a smaller image. Basically, everybody can do this. And 2019 also was the year of the hipster life. So everybody was growing their hipster mustaches, and companies put gaming rooms on their departments and ballenbakken. I'm not sure what the English translation. Ball pits, I guess. And also very shiny MacBook Pros. So all my colleagues back then had MacBooks with at least 8 cores. Yeah, and what do you do as a developer with your MacBook? You open up Visual Studio Code or IntelliJ or whatever. Every now and then you compile a bit, you open some emails and you play some music. Do you really need 8 cores? I don't think so. So I was thinking, can we make use of that hardware, right? I am in need for a lot of hardware for a short amount of time. I cannot get it in our data center, but maybe I can get it on the laptop of our colleagues. Now let's focus on the render step again, where we currently have implemented a synchronous step right after the rendering, but we can also consider adding a REST endpoint. So that after the rendering, and after storing the images on disk, where it's been served out to our customers immediately, we offer the opportunity to get images. So a simple get endpoint, which can be used to get the location, the public location, so the worldwide location where the image can be downloaded, and a post endpoint where you can deliver a smaller image. Now I hear you thinking, who is going to do this? Who is going to make use of these endpoints? Well, the colleagues, right? We have the MacBooks, and we already concluded that a lot of idle hardware is inside these machines. So it started with a kind of a hackathon project, but we created a very small binary, a command line interface tool, especially for this. So a colleague simply installed the Miracle client, that's what we call them, the Miracle, and by running that thing, we enabled this. So the Miracle, after starting up, went to the get endpoint, asking the renderer service to give some work, which returns a URL, a public URL, to a freshly rendered JPEG file, which then the client applied the Gasly algorithm, and when that successfully succeeded, it could use the post and put endpoint to return the smaller image, and then you could replace it. Now there's a nice queue in between, so perfect, right? And the best part, back then we were with 2,000 people, so it's scaled. 2,000 people with 8 cores. Now let's reserve 1 core for their Visual Studio Code, and yeah, there we go. This kind of smells like horizontal scaling. A bit of details about the Miracle tool. We have written it in Go. It cross-compiles, so we provided binaries for Linux, for Mac, and for Windows. It compiles to static binaries, so you don't need dependencies, no OS dependencies, no C libraries, nothing. Just an executable. And we could even include the Gasly binary inside the Miracle binary. So we packaged the Gasly executable inside our thing. We wrapped it around. So it was available as a command line tool, and yeah, so just by running the tool, you could help the company in making images for our customers smaller. At some point, we even added some gamification, and then it really went berserk. Yeah, it is a bit of a strange situation, right? Definitely not recommended on production normally, but yeah, it worked. Yeah, what else to say? People were having fun. We nominated prizes for the top 3 colleagues who reduced the most bytes on disk. And as you can see here, my colleague Mark, he freed up 25 gigabytes of data. So only by applying the Gasly algorithm. Some fun facts. Within a couple of weeks, we applied Gasly to all our image base. On average, 40% smaller images were being sent to our customers, and about 500 MacBooks were constantly crunching and applying the Miracle client. Also, where we used to have a bit of a fight with our operations department about hardware, they suddenly found spare hardware. That's that Mark guy, because he found a couple of racks where he could run the client in a Docker container. And yeah, people liked it. We started to receive merge requests. People improved our dashboarding, and they really wanted to help. It was a nice exercise. Oh, there was even somebody indeed who created a screensaver where he wrapped Miracle in. Yeah. What is now my conclusion? If you have a problem, go running. It can give you some nice ideas every now and then. That's it. Thanks. Are there questions? No. No. Nowadays we run in Google Cloud, so there you just use Cloud Run, and then you scale within a few seconds to multiple pods. So no.
What if the process gets killed before it can return a new image?
When the Miracle client does a get for work, that event is saved in a Redis instance, and I have set a TTL on that. So if someone closes the lid or something goes wrong, the TTL expired, and then somebody else gets the job. We even had funny colleagues who returned other images than the original. Yeah, but we could use the perceptual hashing algorithm to detect the differences, right? Because the threshold should be close to 0. So that was funny. And in the beginning we didn't do that, and then suddenly some unfriendly body pictures showed up. So yeah. Sorry?
The guy from Basecamp and Hey, DHH, he wrote an article on how they're going back from cloud to their own stack. I don't know if you read that?
I haven't read that, but I do recognize this. So at first we hosted all our services. In the beginning, it was like 4 services on an external company, Schuberg Philips, maybe you know it. Then we built our own data center. Now we are converting into the cloud, but we keep on growing, right? We went from a monolith situation to a microservice situation. We went from 3 IT teams now to 300 IT teams with thousands of deployments per day. And at some point, the cloud doesn't scale, so I recognize, but I'm not sure quite yet what the sweet spot is. I'm sure that Netflix is already way beyond that sweet spot, but yeah, it also depends a bit on what kind of stuff you need from the cloud, right? Storage, I would say, don't do it yourself, but compute, for example. If you run your own Kubernetes cluster and you apply a service mesh on top of it, yeah, then why not do it yourself? No more questions? Okay, thank you.